Bam! Mr. Tarrou. In this calculus lesson, we are going to be doing three, not two, but three examples of determining the slope of a curve that's defined by parametric equations. We're going to be discussing whether these curves are increasing and decreasing, which of course is the first derivative, and where they are concave up or concave down, the second derivative. So parametric form of the derivative. We've been reviewing our parametric functions and knocking that dust off of those concepts we learned in pre-calculus. We have if A, smooth curve C, is given by the equations of x is equal to f of t and y is equal to g of t, then the slope of C at that point xy is, well, here you go. The first derivative is kind of what you would think of as very natural. You take the derivative of y with respect to t, you take the derivative of x with respect to t, and as I'm showing this this denominator getting multiplied up here, being multiplied by the reciprocal, and maybe answering the phone? Nope, wife's got it. We can see that our dt's are going to cancel out, and we're going to have that first derivative, that derivative of y with respect to x. Now, when you first see this notation, it looks like our slope of our curve, our first derivative, may seem to be in respect to x, but it is still going to be a function that's going to have an independent variable of t. And that creates a little bit of a curious thing going on here when you go to look at the second derivative. You might just look at a couple of parametric equations and just by instinct, take that derivative of y with respect to t, x with respect to t, and just know that it's going to be your dy dx. But how do you find a second derivative? How do you take the derivative with respect to x, kind of, because derivatives are slope, and that's a change of y over a change of x. So how do you take the derivative of that first derivative? And when you write the notation like this, it seems like we should have an independent variable of x. But no, we're going to have an independent variable of t, or maybe theta if you're talking about trig functions. What's in the middle here? We need to do something to bring in that variable of t into our derivative notation. Now, how that's going to look is this. We're going to take the derivative with respect to t, and write it correctly, of our first derivative, dy over dx. Now remember, that first derivative is going to be in terms of t, so that's good. But I need this sort of d over dx, right? I need a derivative, right? This first derivative notation doesn't have any t's in it. So that's going to be over, now if I write this, dx dt, we're going to take the derivative with respect to t, we're going to take the derivative of the first derivative with respect to t, but we're going to show that as over dx dt, because of course if you look at just this notation here, this derivative notation, if we, because we need, again, bring in that variable of t into our notation, so it kind of makes sense as we try and find the second derivative. If I take this dx dt in the denominator and multiply by the reciprocal, at least in terms of the notation here, those dt's will cancel out and we see that d over dx. That's going to come out to be, that's the work we're going to do to find the second derivative. Now, if you want to find the third derivative, well, then you're going to take the derivative, which appears to be in this sort of, respect to x, because we don't have any variables of t in our derivative notation, but that is going to be taking the derivative of the second derivative is going to give us a third derivative. We're not finding third derivatives in this example because we're just going to talk about, or this video, because we're just talking about increase and decrease and concavity. But it would be kind of what you would think. We're going to take the derivative with respect to t of the second derivative, and have again that dx dt notation, or the derivative of x with respect to t, in our denominator. And that will give us our third derivative. Third derivative. And if you want to find the fourth and fifth derivative for whatever reason in your problem, you just keep this process going as you go along. Now, we're going to take a look at those three examples starting right now, and maybe clarify this notation as you see me go through this work. No. So, starting off relatively easy, we have our first example. We have our parametric equation defining the horizontal movement. X is equal to basically the square root of t. We have our parametric equation describing the vertical movement. Y is equal to 5t minus 2. And we're going to find the slope, the first derivative, and discuss the concavity, the second derivative, at the given value of the parametric, of the parameter, which is, of course, t equals 1. So, let's find that first derivative, shall we? So we're going to do the derivative of y with respect to t, and of course that's just going to be 5. We have the derivative of x with respect to t, and we're looking at bringing the 1/2 down, so we have 1/2 t, reduce that exponent by 1, so we have 1/2 t to the negative 1/2, which makes our first derivative dy dx equal to, well, dy, which is 5, over what? Now this has a negative exponent, so I'm going to go ahead and write this as 1 over 2 times the square root of t. And with this being our main fraction bar, we're going to bring that fraction in the denominator up, multiply by the reciprocal, and we have 5 times 2, which is 10, square root of t. So there's our first derivative. So what is this curve? What's the curve defined by these two parametric functions? Is it increasing or decreasing when t is equal to 1? Well, our first derivative, dy dx, notice no notation of t in there, but we're going to find that derivative when t equals 1, right? Because slope is change in y over change in x, not some kind of change in t. So we have our first derivative when t is equal to 0. Well, we have 10 times the square root of 1, which is just simply equal to 10. So our first derivative is greater than 0 when t equals 1. Therefore, the curve is increasing. Okay, now what about that second derivative? The second derivative, let's get a different colored chalk here. The second derivative is the derivative with respect to t of dy over dx over dx dt. Okay, so again, you can see that if we were to bring this bottom fraction up and multiply, if you will, or bring it up and show that as dt over dx, the dt's would cancel out and we'd have dx. So we talk about that sort of change in y over change in x in terms of the second derivative. So, and see here, our first derivative is in terms of, okay, let's try this. Our first derivative is in terms of t. So we're going to do the derivative with respect to t of 10 times t to the 1/2, because I don't like working with derivatives with radical notation. Just wrote that to make it look neat. Over dx dt. Now where was that? Dx dt is our 1 over 2 times t to the 1/2 power. So we got 1/2 times 10 is equal to 5. Reduce that power by 1. Now we're not taking the derivative down here. This is dx dt. We're just writing that answer from earlier on in our work. So don't take the derivative of the denominator again. That's going to be 1 over 2. I feel like I made a mistake here somewhere. Oh, yes, right there. No. Where am I at? Hold on just a second. That's what happens when you start thinking ahead and not actually just paying attention to each individual step. I started thinking I was making a mistake here. We do have that 2 times t to the 1/2 power. I started visualizing this coming up and multiplying these together, and yeah, we haven't taken care of that negative exponent. So, or at least I wasn't doing that in my head. Okay, at any rate, we have 5 times t to the negative 1/2 times, bringing this up, times 2 times t to the positive 1/2, and 5 times 2 is equal to 10, of course, and when you multiply like bases, the negative, which I wasn't catching in my head, so I thought I was making a mistake because I know this is going to cancel out. Negative 1/2 plus 1/2, of course, is going to be 0. T to the 0 power is 1. So our second derivative, yeah, well, I showed the second derivative notation, but this is our second derivative. Bam. So not only is our second derivative basically, because I want to discuss concavity. So not only is our second derivative positive when t is equal to 1, but actually our second derivative is always positive. So this the curve defined by these parametric equations is always going to be concave up everywhere. So just again right here we see that the second derivative is greater than 0. So therefore the curve is concave up. Really, it's concave up for all values of t, because it's always going to be positive, but this is specifically about when t is equal to 1. And that is the end of our first example. They're going to get a little more complicated as we go through examples 2 and 3, but that's coming up right now. So here we have the second example. Same directions, just got some trig in it this time, which is going to complicate things, but you know, we're in Calc 2. We should certainly be able to do this without too much trouble. We're going to do dy d theta, take the derivative of y with respect to theta, and we've got, well, of course, the derivative of tangent is secant squared, so we have 2 secant squared theta. And dy or dx d theta is going to be derivative of a constant is 0, and the derivative of secant is secant theta tangent theta. Now, setting up our first derivative as dy d theta over dx d theta. We get dy dx is equal to 2 secant squared theta over secant theta tangent theta. And we need to move into the second derivative, so I want to simplify this. And that is going to be, I'll just write it over here and then erase it. We have 2 over, secant, of course, is the reciprocal of 1 over cosine, so we have 2 over cosine squared theta over, now we have 1 over cosine theta times sine theta over cosine theta. Good. And just making sure I don't make any mistakes. And then we've got 2 over cosine squared theta over sine theta cosine squared theta. The numerator and denominator both have exactly the same denominator, so we end up with 2 over sine theta, or 2 cosecant theta. Okay, so is the curve defined by these parametric equations increasing or decreasing when theta is equal to pi over 3? Well, let's see. Well, I know this is going to take up some room, so let me just put this right down here. dy dx when theta is equal to pi over 3 is equal to 2 times the cosecant of pi over 3. Well, the sine of pi over 3 is square root of 3 over 2, so we're looking at, for cosecant, 2 over square root of 3, so we're looking at 2 square root of 3 over 3 times 2. So our first derivative is positive at pi over 3, so our function is increasing when theta is equal to pi over 3. Now what about that second derivative? And let me just check this because when I talk and write at the same time, I have a tendency to mess things up more than I would like to admit. Ah, yes. All right. So for our second derivative, see, in class, all my students get to correct my mistakes. I'm just really trying to make sure that they're paying attention. On camera, you guys, well, you do sometimes on YouTube tell me, hey, you made a sign error, you wrote something silly, you said this, you wrote that, and then I have to pull the video and repost it. Since they took away our annotations. Okay, so our second derivative is going to be the derivative with respect to, well, let's see here, right? Our first derivative is in terms of theta. So d theta of dy dx, which is, of course, dy dx is 2 cosecant theta. So again, the derivative with respect to the variable, which is the independent variable for our parametric equations, usually it's t, but trig functions it's theta, over dx d theta. Well, dx d theta is secant theta tangent theta. Okay, so taking the derivative of the numerator with respect to theta, we have, and we'll go down here. Actually, there, that's what we're finding, the second derivative. So we have the derivative of cosecant is negative cosecant cotangent, so we're looking at negative 2 cosecant theta cotangent theta. And that is over secant theta tangent theta. And that is negative 2, that's 1 over sine. Cotangent is cosine theta over sine theta. Our denominator is 1 over sine theta over cosine, secant's 1 over cosine. Cosine theta. And we have got negative 2 cosine theta over sine squared theta. And here we have sine theta over cosine squared theta. Flipping that up, we have that our second derivative is equal to, well, cosine over sine is cotangent, so we have negative 2 cotangent cubed theta. So is the curve defined by these parametric equations concave up or concave down? Well, let's plug in our theta of pi over 3. Okay, so the tangent of pi over 3 is square root of 3, so the cotangent of pi over 3 is the square root of 3 over 3. Now it's cubed, so we're looking at negative 2. We're really just looking to see if it's positive or negative, but just to get that second derivative out, square root of 3 times square root of 3 is 3. We got one more square root of 3 left, so we're looking at negative 2 times 3, square root of 3 over, that's going to be 27. Canceling this out, we get 9. And the second derivative at pi over 3 is going to give us an answer of negative 2 square root of 3 over 9. So our second derivative is negative when pi over 3, when theta is equal to pi over 3, therefore it's concave down. Now, I hope that you saw me add a little bit of information there at the end. Like if you were asked to find the tangent line, of course, you need a point and a slope. If it asked you something like, you know, at what point along the curve or at this point at the curve, is it increasing, decreasing? I don't know, just to make sure that you remember, of course. I certainly hope so. What is the point on the graph here at pi over 3? Well, that's going to be x is equal to 2 plus the secant of pi over 3. So our x-coordinate is going to be 2 plus the cosine of pi over 3 is 1/2, so that's going to be 2. So our x-coordinate is 4. The y is going to be 1 plus 2 times the tangent of pi over 3. That's going to be 1 plus 2 square root of 3. And so that's just you know, the point. When at that point on the curve, it is increasing and concave down. All right, last example coming up right now. We're going to find intervals, determine the t interval on which the curve is concave down or concave up. It'll also involve trigonometric functions, specifically, again, sine and cosine. And for our last example, we're going to determine the t intervals on which the curve is concave up or downward, or concave upward. Really, it's still got trig functions, very similar to the previous example. I'm just throwing this in as a little bonus example. Slightly different wording. And after seeing these first two examples, can you do this question on your own? Now, of course, if we're going to be finding intervals, not testing what, you know, if it's concave up or concave down just at a point, but an interval, right? We're going to find the second derivative. We're going to identify critical values and set up some, you know, marked intervals along a number line, specifically between 0 and 2 pi, and just simply analyze the sign of our second derivative along those intervals. And those critical values are going to be where your derivative, in this case second derivative, is equal to 0 or undefined. So I'm just going to step off, reveal the solution, you know, one step at a time, or every 5 seconds give another step. Pause it, try it on your own, just make sure you've got this down pat, and that will be the end of our lesson. Bam! I'm Mr. True. Go do your homework.